our calorimetry experiment, most of what we learned was how to do the problems. It's a lot of math. The main equation is this one, where Q is heat, S is specific heat, mass, and delta T, change in temperature. Your instructor may write this in a different order, but it's the same thing. And then specific heat, we will give you the constant for the specific heat of water. It will help you if you know that specific heat can only be a positive number. And the other thing we use is that if you have a calorimeter, the change in enthalpy for the reaction is going to be the same number but opposite sign of the Q for the calorimeter, the water, or the solution, whatever is changing temperature. Anyway, so there's two kinds of problems. Let's look at our first one, which involved the metal. The idea in this experiment was that we had some water in a calorimetry cup and we poured some hot metal in it. We had heated the metal in a boiling water bath, so the metal was at 100 degrees. And we also know what mass of metal that we used. And when we did that, we watched the temperature of the water in the cup, and it will warm up for a while and then it'll steady out. And so the temperature, we have a T1 for this is for the water, and a T2 for the water. But a very important thing to note is that the T2 for the metal is the same as the T2 for the water, because we assume that we wait till we get to thermal equilibrium, which is where the two temperatures are the same. Okay, and so what we can do, if we look at this equation, we have a lot of the numbers for the water and not so much for the metal, so we can start with the water. So I'm going to make sure that all the numbers that I put in here are for the water. So the specific heat, like I said, that'll be given on the test. The mass of the water, we may give you the milliliters of water. Just assume 1 gram per milliliter for density. This one I actually gave the mass. And then for T2 minus T1, so for delta T, always kind of watch your sig figs on this part, because sometimes you lose quite a few digits. We didn't on this one. Do keep track of your sig figs. This has 3, but do carry extra digits on these problems until the end. When we ask you, so if we asked you for the Q of water, right here you would round it to 2.72 times 10 to the 3rd joules. But if you're going to the next part, you want to carry more digits as you go. So, okay, and signs are very important when you're calculating Q, because if it's gaining heat, it's positive. If it's losing, it's negative. And that can really change your answers and what's available on multiple choice. Anyway, so I've got my Q for my water, and the thing to know is that my Q for my metal is going to be the same number but the opposite sign. And that's because however much heat the metal is losing, the water is gaining. So Q is positive for the water and negative for the metal, but it's the same number. So then when I go down here and this time I'm putting in all the numbers for the metal, I'm going to take that Q for the water and change the sign. I'm solving for the specific heat of the metal. I have a mass for the metal. And then another trick I need to note, and we said this earlier, for our delta T, we want T2 minus T1. Well, T1 is easy. It was the 100 degrees. But T2, we need to know that this T2 is the same as the water, because we assumed that heat was transferred until they were the same temperature. So T2 for the water was 35. That means that when you do this part, you'll get a negative number, which you should, because Q for this is a negative number, which that's where that comes in. Okay, and a very important thing to note that may help you is that specific heats have to be positive. And so I can see my negative signs canceled out here because I can't keep track of that. But anyway, so that's how you do the specific heat. Let's look at the other part of this experiment involving the reaction where we dissolve the salt. And this one, we added some salt to water and stirred. And so the reaction is not really confined to a special compartment or anything. It's all mixed together. And when it's mixed, the thing that's warming or cooling is not just the water, but it's also the salt that's dissolved. So on this one, instead of looking at just what the temperature change is for the water, we look at the temperature change for the solution. And that matters because that affects the mass a little bit. So anyway, we can see with our usual equation that we could fill in most of the numbers for the solution. So we'll start with that. We don't know the Q for the solution. It will tell you that to assume the specific heat for water for the solution. For the mass of the solution, this is where you need to add those two numbers. So on this one, sometimes the solution cools and sometimes it warms depending on your reaction. We still use T2 minus T1, and we'll get our Q for the solution. Watch your positive and negative signs. This part is where we get our negative sign. And it is also what limits our sig figs. If we use our subtraction rule correctly there, we see it only goes one past the decimal, so it limits our sig figs. So if we had to write an answer for the Q for the solution, we would write 2 sig figs here. We would round it off 1.3 times 10 to the third joules, and of course negative 1.3 times 10 to the third joules. Okay, but it asked for the heat of the reaction or change in enthalpy for the reaction in kilojoules, not joules, per gram of salt. So what we're going to do, first of all, we need to realize that the heat of the reaction, or change in enthalpy for the reaction, is equal to the same number but opposite sign as the Q for the solution. So we're going to change the sign. And so that is our change in enthalpy for the reaction, but we're supposed to get it in kilojoules per gram of salt. And so what we do is we take that and we want to say per gram of salt dissolved. So we go up and we find our mass of our salt. And we divide it there. And then the other part we do is it asks for kilojoules, so we'll convert our joules to kilojoules. And we just have 2 sig figs, so okay, and we may ask you, is that endothermic or exothermic? This is endothermic because that's positive. That's why it's so important to watch the signs, because that changes whether it's endothermic or exothermic. So to watch all the signs on stuff, what I suggest you get in your head is this pattern. If the solution cools, that means the Q for the solution is negative, and the change in enthalpy for the reaction will be positive, and that will be an endothermic reaction. If the solution warms, the Q for the solution will be positive because it's accepting heat. The enthalpy will be negative because it's losing stored heat, and the reaction will be exothermic.